Hello, this training is a conversion guide where I will go through various features of the Zynq UltraScale FPGA and compare them to the Agilex 5 FPGA with the intent on learning how to migrate your design from the Zynq FPGA to the Agilex 5 FPGA. Let's begin. Here is the agenda for the course. I will go over hardware comparisons, primitive conversions, IP cores, the clocking network, I/O, embedded processor comparisons, and the memory interfaces. First, the hardware comparisons. Here are some of the terms for the two FPGAs: the processing system, PS, and hard processor system, HPS, refer to the same type of hardware that exists in the FPGAs, namely the hardwired ARM processors. The programmable portion of the FPGAs are referred to as programmable logic, PL, and FPGA fabric logic. To build a system for the Zynq UltraScale FPGA, you use Vivado IP Integrator. The equivalent tool to use for the Agilex 5 FPGA is Platform Designer, which would be used in conjunction with the Quartus software. If you are unfamiliar with the Quartus software or Platform Designer, we offer many trainings free of charge to help you shorten the learning curve. The Hardware Manager and System Console are terminal-like tools to connect to your FPGA system through a JTAG port where you can read and write values to registers inside of the IP that support such a connection. Lastly, Zynq's block RAM or BRAM is analogous to on-chip memory. Here is a comparison of the ARM cores that you will find in both FPGA families. Note that there is a D series and an E series for the Agilex 5 FPGAs. The ARM cores that you find in the Agilex 5 devices are at least as capable as the ARM cores that you find in the Zynq UltraScale devices. The Zynq FPGAs will have 4 ARM cores and the Agilex 5 also has 4 cores, 2 Cortex-A55 and 2 Cortex-A76. Pause here for a moment if you wish to glance at the other differences. I will not go over in detail the differences between the IPs offered for the different processor systems, so feel free to pause the video to examine in detail any aspect that you are interested in. And finally, here is a comparison of the various ARM cores that are found in the FPGA families with the Cortex-A53 found in the Zynq devices, and the Cortex-A55 and A76 found in the Agilex 5D series and E series devices. If you want an idea on how to convert gate usage from one vendor to another, here is a rough estimate to get you going. AMD has slices and Altera has ALMs, which means Adaptive Logic Module. A slice has one 6-input LUT, and an ALM has one 8-input LUT. Both vendors' LUTs can be configurable to accommodate different input sizes, but roughly there are about 1 ALM worth of LUTs to about 1.3 AMD 6-input LUTs. Next, let's go over converting instantiated primitives. When migrating a design, you must convert common AMD Xilinx primitives to the Altera FPGA equivalents. Primitives perform dedicated functions in the device and implement standards for I/O pins in AMD Xilinx devices. You can select a particular I/O standard to use by making that assignment in both Vivado and Quartus software. You can also instantiate a primitive for the desired I/O standard in AMD Xilinx FPGAs. If the input or output buffer primitive is instantiated, all you need to do when migrating your design to an Agilex 5 device is to remove the primitive instantiation and place an appropriate I/O standard assignment. In the event that other more complex primitives have been instantiated, such as the DSP48, then understanding the functionality used in the primitive and finding a corresponding FPGA IP will be key. A straightforward way to instantiate some FPGA primitives exists in Quartus Software's Text Editor's Templates options. Clicking on the Templates button brings up all sorts of templates, including primitives. Find the desired primitive and click the Insert button. The selected primitive will now be inserted in your HDL code. Primitives are resources available inside of the FPGA that you can directly instantiate. When migrating a design, you must convert all Xilinx primitives that you have in your project to the FPGA equivalents. You can either instantiate an equivalent Intel FPGA primitive, create a functionally equivalent IP, or infer the resource in your HDL code. Primitives perform dedicated functions in the FPGA and implement standards for I/O pins in Xilinx devices. Primitive names are standard. Please refer to FPGA Application Note 307 for more information on replacing primitives. Let's talk about converting your IP cores. Here is a list of some of the more popular IP and their counterparts. The user guides for the FPGA IP are listed alongside the IP. When replacing a Xilinx IP with an Intel FPGA IP, search for the potential IP using keywords, or if you know the name of the Altera FPGA IP, search by name directly. The IP search field can be found in the top right in the Quartus software GUI. Type in the search parameter to find the desired IP. When you have found your IP, double-click on it to start with the parameterization. The GUI that launches is called the IP Parameter Editor. Start by typing in the name you want for the particular variant of the IP and then click the Create button. Next, the GUI will come up where you can enter in the IP's parameters. Many IP will have multiple tabs for the parameters. The details of the parameters can be found in the GUI. When you are done configuring your IP, click on the Generate HDL button. The parameterization page that comes up next will allow you to select your language preference for both the synthesis and simulation files. This page also offers other parameters for you to modify according to your project's needs. Now that the IP is created, the IP component will be visible in the Quartus Software Project Navigator tab. Also, some of the IP's files will be visible in the Files tab as shown here. Now I will go over the differences in the clocking. This section will first guide you through the differences between Zynq and Agilex 5 clocking architecture and network. This understanding will be crucial for effectively utilizing the conversion tables provided for your design. Next, we will explore the conversion tables, detailing the dedicated hardware resources in Xilinx Zynq and outlining their corresponding parameters to be enabled in Quartus for the Agilex 5 platform. Specifically, these conversion tables will cover global clocking primitives, clock buffers, clock management tile components, Zynq UltraScale plus MPSoC clocking architecture. The Zynq UltraScale plus MPSoC provides dedicated resources for clock management, including the clock management tile, which is responsible in generating the operating frequencies, noise minimization, and latency corrections. The clock region in the Zynq device allocates the required dedicated clocking and routing. The clock routing is then responsible in distributing the signals within the clock regions. The global clock buffers provide the clock signals for the design. The transceiver tile blocks manages the clocking for the I/O signals. While this dedicated architecture offers users high control and flexibility over managing clocking, it can also lead to a more complex design approach compared to simpler clocking schemes. This complexity can potentially result in routing challenges during the design process. Agilex 5 FPGA and SoC devices have a synthesizable clock tree network, which means that the Quartus software will automatically build the clock network that distributes clock signals throughout the device. This feature simplifies the design process as users only need to specify clock source, clock outputs, desired clocking, and PL parameters. The Quartus software then handles the heavy lifting by configuring the dedicated FPGA resources, constructing the optimal clock tree based on the design and user-defined timing constraints. This automation streamlines clock network design, reducing complexity and potentially improving performance due to the clock tree synthesis capabilities. While Quartus automates clock network creation in Agilex 5, understanding Zynq's dedicated clocking resources can aid in interpreting the conversion tables provided. This table outlines commonly used Zynq primitives and their corresponding parameter settings in Agilex 5. These settings achieve similar functionality to Zynq's clock buffers within the Agilex 5 architecture. You can access and configure these parameters through the Clock Control FPGA IP within the Quartus IP catalog. Building upon the understanding of Agilex 5's automated clock network construction, this table delves into commonly used clock buffers in Zynq and their corresponding parameter settings in Agilex 5. These settings guarantee that the functionality of the clock buffers remains consistent across both platforms within the Agilex 5 architecture. To access and configure these parameters, navigate to the Clock Control FPGA IP within the Quartus IP catalog. To configure custom PLLs for your Agilex 5 design, utilize the FPGA IO-PLL IP, accessible within the Quartus IP catalog. This IP core replaces Xilinx MNCMs, offering greater flexibility and control over clock generation. For dynamic reconfiguration of your PLLs in conjunction with the EMIF interface, leverage the EMIF calibration IP. This IP, also located in the Quartus IP catalog, ensures accurate clock synchronization for optimal performance. In this section, I will discuss the differences in the I/O. For the Zynq UltraScale Plus, the groups of I/O are called high performance, high range, and high density, whereas the Agilex 5 FPGA has high speed and high voltage. When migrating from Zynq UltraScale Plus to Agilex 5 devices, the supported I/O feature varies. Some key differences are the voltage support in each different bank type and the bank size. The I/O voltage in HPIO, HRIO, and HGIO are per bank basis, while the Agilex 5 I/O voltage granularity is per sub-bank basis, allowing higher placement flexibility. HPIO bank voltage has a better compatibility with Agilex 5 HSIO, and HRIO is a better match with Agilex 5 HEIO. However, the supported voltage is still not a direct match. Therefore, a voltage redesign and I/O standard reassignment is needed. The I/O types are mainly comparable between Zynq UltraScale Plus and Agilex devices, but the I/O standard varies. Refer to the I/O standard comparison table to select the best match for the I/Os used in Agilex 5 devices. This table is in continuation of I/O feature comparison between Zynq UltraScale Plus to Agilex 5 devices from the previous slide. While most of the features supported are comparable between Zynq UltraScale Plus and Agilex 5 devices, the supported feature varies across I/O standards. The key difference in this table is the I/O delay chain support in Zynq UltraScale Plus. MPSoC can be both static and dynamic, but Agilex 5 only supports static delay chains. After migrating to an Agilex 5 device, ensure you perform IBIS H-SPICE simulation to verify your interfacing signal quality. This table provides comparison of the I/O standard support across different bank types in Zynq UltraScale Plus and Agilex 5 devices. Each I/O standard has its individual voltage and feature supports. Ensure that you redesign your voltage supplies and I/O placement when migrating from Zynq UltraScale Plus to Agilex 5 devices. To create I/O assignments, both Vivado and Quartus software can import or export CSV files. For the Vivado flow, all location assignments are stored in an XDC file, which is a superset of the Synopsys Design Constraints, or SDC, and location assignments. For the Quartus software, any type of location assignment can be found in the Quartus settings file, or QSF. The QSF is tickle-based and also contains any project type setting such as a compiler effort level. The Vivado tool to help facilitate I/O assignments is the I/O planning. The analogous tool for Quartus software is the pin planner, which is a floor planning type tool where you can not only assign pin locations, but also the I/O standard that you are interested in. After you are done with Pin Planner, you can then export all of your placements in the project's QSF file. In Quartus, you can also choose to make I/O assignments in the Assignment Editor, which is a spreadsheet-like tool where you can find your desired assignment and assign the appropriate value for that assignment. As with Vivado's I/O planning, where you can make assignments in a spreadsheet format, you have the same capabilities in Pin Planner. This portion of Pin Planner is immediately available in the tool, in a section called the All Pins list. The assignment editor is similar to the look and feel of the All Pins list section in the Pin Planner, but is a bit more generic to be able to accommodate the variety of assignments that are not only location assignments, but other project assignments and compiler settings. Be sure to reference the Agilex 5 General Purpose I/O User Guide and Application Note 982 for more information. I will now go over the embedded processors comparisons. Over the next number of slides, I will present some differences between the processor systems on the Zynq UltraScale Plus parts and the Agilex 5 SoC parts. I will not enumerate all of the differences, but I will touch on what I consider to be the highlights. In the Agilex 5 SoC, we have updated faster ARM cores with larger cache sizes and a greater variety of external memory support. Both systems offer a variety of peripherals and secure boot methods, so be sure to scan through what is offered. The Agilex 5 SoC does offer a configuration method where you can either activate the processor first and then configure the FPGA logic, or configure the FPGA logic and then bring up the processor system. This next 4 slides show the component-level comparison for the features supported by the Zynq processing system versus the Agilex 5 hard processing system. The table maps components in Zynq PS to equivalent components in the Agilex 5 HPS. To help you understand better the equivalent components that you can expect in Agilex 5 HPS and migrate over from Zynq PS. You can refer to the Agilex 5 Hard Processor System Technical Reference Manual for more information about specific components. Feel free to pause on the next 3 slides if you wish to examine the contents in more detail, as I will show them only briefly. An equivalent IP to the Zynq UltraScale Plus processing system Logicore IP core is the Hard Processor System Agilex 5 FPGA IP and Altera Quartus Platform Designer tool. You can refer to the Component Reference Manual to learn more on how to configure the IP. There are 4 configuration tabs available in the Zynq PS IP, and the following few slides will briefly walk through their equivalent configuration tabs and tools provided by the Altera Quartus software. I/O configuration can be done using the HPS IP and Platform Designer under Pin Mux and Peripherals tab, Assignment Editor and Pin Planner in the Quartus. For more information, refer to the manuals and user guides listed on this slide. Clock configuration can be done in the HPS IP under HPS Clocks, Resets, Power tab. Various clock settings can be configured for the input and PLL clocks. For DDR configuration, you will need to configure two components, the HPS IP under SD-RAM tab and the standalone EMIB for HPS IP. The upcoming section, Fabric Embedded Memory Interface, goes over the HPS EMIB migration. Please refer to that section for more details. You can configure the FPGA HPS interface configuration on the tab with the same name. Here is a mapping of the interfaces available in the Zynq PS, with their equivalent bridge interfaces in the Agilex 5 HPS. In a Zynq UltraScale Plus MPSoC device, there is a boot ROM for initial bring-up of the device. The configuration and security unit processor uses the code in the boot ROM. In this configuration stage, the boot ROM interprets the boot header to configure the system and load the processing system's first-stage bootloader code into the on-chip RAM in both secure and non-secure boot modes. The boot header defines many boot parameters, including the security mode and which processor should execute the ATSBL. The boot header parameters can be found in the Zynq UltraScale Plus Device TRM User Guide 1085. During boot, the CSU also loads the PMU user firmware into the PMU RAM to provide platform management services in conjunction with the PMU ROM. The PMU F2 must be present in most systems for the Xilinx-based ATSBL and system software. The loading of the FBSL before the PMU firmware is the default configuration. Some systems will switch the order and have the PMU firmware loaded first, so there might be other diagrams showing the ATSBL and the PMU firmware switch. Secure Device Manager Boot ROM. SDM samples the M-cell pins to determine the configuration scheme and boot source, and establishes the device security level based on eFuse values. SDM initializes the device by reading the configuration firmware from the boot source, authenticates and decrypts the configuration firmware, and starts executing the configuration firmware. Configuration management firmware running on SDM will load the ATSBL, which is you boot SPL into HPS OC RAM, then bring HPS boot core out from reset. U-boot secondary program loader loads the SSBL, which is ARM trusted firmware BL31, and U-boot proper into DDR. U-boot SPL jumps to ATFBL31. ATFBL31 sets up the generic interface controller EL3 environment and initializes PSI services. ATFBL31 jumps to U-boot proper. U-boot proper loads Linux into DDR. U-boot then jumps to Linux. U-boot proper and Linux can access SDM FPGA features via ATFBL31 through ARM Secure Monitor Call. Secure Device Manager Boot ROM. SDM samples the M-cell pins to determine the configuration scheme and boot source, and establishes the device security level based on eFuse values. SDM initializes the device by reading the configuration firmware from the boot source, authenticates and decrypts the configuration firmware, and starts executing the configuration firmware. ARM trusted firmware BL2 and BL31 will be used as bootloader to load Zephyr in the SoC FPGA. Configuration management firmware running on SDM will load the ATSBL, which is ATFBL2 into HPS OC RAM, then bring HPS boot core out from reset. ATFBL2 loads the SSBL and OS, which is ATFBL31 and Zephyr into DDR. ATFBL2 jumps to ATFBL31. ATFBL31 sets up GIC, EL3 environment, and initializes PSI services. ATFBL31 jump to Zephyr. Zephyr can access SDM FPGA features via ATFBL31 through ARM Secure Monitor Call and Maillocks. After the hardware project for the HPS is compiled using the Quartus Prime software, the configuration files are generated by the Programming File Generator. The hardware handoff SOF file insulates software developers from the changes that might occur on the hardware side during development. The configuration files contain the following components which are required for configuring the hardware design. This table provides a description of the different components contained in the configuration files required for configuring the hardware design. The SOF file contains all of the configuration information to program the FPGA with the design that you created. The Quartus software contains the boot ROM that initializes the SDM. The HPS software is the first stage bootloader, second stage bootloader, OS, and your software application. The configuration files are created by the Quartus Prime Programming File Generator, using the following inputs: SOF file, first stage bootloader hex file, and Quartus Prime firmware. U-boot and ARM-trusted firmware bootloaders are supported. Agilex 5 supports several different configuration methods. Configuration over JTAG, configuration from QSPI, configuration over AVST, configuration via protocol. This next number of slides describes how to create the configuration files for all these configuration methods. JTAG configuration, where the FPGA logic is configured first. 1. Compile hardware project with Quartus Prime to obtain the SOF file. 2. Compile the HPS FSBL source code to obtain the HPS FSBL hex file, or use a precompiled HPS FSBL hex file. 3. Add the HPS FSBL hex file to the SOF file to obtain the HPS SOF file. SOF files resulted from compiling hardware designs that have HPS instantiated cannot be used directly to configure the device. 4. Use the Quartus Prime programmer to configure the device over JTAG with the resulted HPS SOF file. The required firmware to run on the SDM must be downloaded on the device by the Quartus Prime programmer. Here is the sequence when the HPS is configured first. 1. Compile hardware project with Quartus Prime to obtain the SOF file. 2. Compile the HPS FSBL source code to obtain the HPS FSBL hex file, or use a precompiled one. 3. Use Programming File Generator to create the following files. Raw binary file contains the small phase 1 configuration bit string. Core RBF file contains the typically much larger phase 2 configuration bit string, to be used by HPS software later to configure the fabric. With QSPI configuration, when the FPGA logic is configured first. 1. Compile hardware project with Quartus Prime to obtain the SOF file. 2. Compile the HPS FSBL source code to obtain the HPS FSBL hex file, or use a precompiled one. 3. Use Programming File Generator to create the following files. JTAG indirect configuration file contains the configuration bit stream to be written to flash and SDM helper image, used by the Intel Quartus Prime programmer to write the bit stream to flash. Optional, raw programming data file contains the configuration bit stream in plain binary format, can be written to flash with a third-party programmer, such as U-boot. Optional, map file describes the actual flash usage in human-readable text format. 4. Use the Quartus Prime programmer to write the JIC image to QSPI flash. Alternatively, use a third-party programmer to write the RPD image to flash. 5. Set mcell to QSPI, then power up, power cycle, or toggle in config to cause the device to configure itself from QSPI. 6. FPGA device is configured, and after init done, the HPS FSBL is also executed. QSPI with HPS booting first. 1. Compile hardware project with Quartus Prime to obtain the SOF file. 2. Compile the HPS FSBL source code to obtain the HPS FSBL hex file, or use a precompiled one. 3. Use Programming File Generator to create the following files. HPS JTAG indirect configuration file contains the small phase 1 configuration bit string and a small SDN helper firmware image used by the Quartus Prime programmer to write the bit string to flash. Optional, HPS raw programming data file contains the small phase 1 configuration bit stream in simple binary format. Can be written to flash with a third-party programmer, such as U-boot. Core RBF file contains the phase 2 configuration bit string to be used by HPS software to configure the FPGA fabric. Optional, map file describes the flash placement and usage in human-readable text format. Note: the phase 1 and phase 2 configuration bit streams must be created by the exact same Quartus Prime Programming File Generator version, including the same firmware patches. Also, the phase 1 and phase 2 configuration bit streams must have the same HPS AO settings, including the HPS DDR settings. If these conditions are not both met, the phase 2 configuration fails. Here is the sequence for FPGA first configuration over Avalon streaming. 1. Compile hardware project with Quartus Prime to obtain the SOF file. 2. Compile the HPS FSBL source code to obtain the HPS FSBL hex file or use a precompiled file. 3. Use Programming File Generator to create the raw binary file which contains the configuration bit string in binary format. The FPGA needs to be configured on the board to set MCell pins to the AVST mode. Power up, power cycle, or toggle in config on the FPGA. Use an external initiator connected over AVST to configure the device using the RBF file. Here is the sequence for the HPS boot first over Avalon streaming. 1. Compile hardware project with Quartus Prime to obtain the SOF file. 2. Compile the HPS FSBL source code to obtain the HPS FSBL hex file or to use a precompiled one. 3. Use Programming File Generator to create raw binary file which contains the small phase 1 configuration bit string. Core RBF file which contains the typically much larger phase 2 configuration bit string to be used by HPS software to configure the FPGA fabric after the HPS is online. The FPGA device needs to have its MCell pins in the AVST mode, then power up, power cycle, or toggle in config on the device. Use an external initiator connected over AVST to configure the device using the phase 1 bit string. HPS software starts running, beginning with HPS FSBL. Later, HPS software configures the FPGA fabric by using the phase 2 core RBF bit string. Here is the configuration via protocol sequence. 1. Compile hardware project with Quartus Prime to obtain the SOF file. 2. Compile the HPS FSBL source code to obtain the HPS FSBL hex file or use a precompiled file. 3. Use Programming File Generator to create the following files. Peripheral JIC file, which contains the initial configuration bit string, including peripheral configuration data and SDM firmware, and a small SDN helper firmware image used by the Quartus Prime programmer to write the bit string to flash. An optional peripheral RPE file, which contains the same initial configuration bit string as the peripheral JIC file in simple binary format. This file can be written to flash with a third-party programmer, such as U-Boot. Core RBF file, which contains the FPGA configuration data, to be used by PCIe host software later to configure the FPGA fabric. The HPS FSBL is included in the core RBF file, an optional map file which describes the actual flash usage in human-readable text format. The FPGA device is configured from the initial peripheral bit string from QSPI Flash, which brings up the PCIe interface on the FPGA. The PCIe host later configures the core fabric over PCIe. This includes downloading and running HPS FSBL. When using CDP, only the FPGA configuration first mode is supported. The very first part of the FPGA bring-up process is initializing the Secure Device Manager. The SDM is loaded with its firmware, which was inserted into the SOF by the Quartus Prime Programming File Generator. Once the SDM is initialized, the process of loading bootloaders and bit streams starts. The first stage bootloader is the first boot stage for the HPS. In FPGA configuration first mode, the SDM extracts and loads the FSBL into the on-chip RAM of the HPS. The SDM releases the HPS from reset after the FPGA has entered user mode. After the HPS exits reset, it uses the FSBL hardware handoff file to set up the clocks, HPS dedicated IOs and peripherals. You can create the FSBL from one of the following sources. U-Boot secondary program loader, which Intel provides the source code for on GitHub, and the ARM trusted firmware, which is also available on GitHub. The second stage bootloader is the second boot stage for the HPS. The first stage bootloader initiates the copy of the second stage bootloader to the HPS SD-RAM. The second stage bootloader typically enables more advanced peripherals, such as Ethernet, and supports command line interface. You can create the SSBL from U-Boot or the ARM trusted firmware, both of which can be found on GitHub. The operating system is the third boot stage for the HPS. The second stage bootloader loads the operating system stage into SD-RAM. The OS can be Linux, Zephyr, or bare metal. The OS executes from SD-RAM. The last boot stage is the application that runs on the OS. To summarize the last few slides that we have just seen, here is the sequence of events that happens during the configuration of your Agilex 5 SoC FPGA. In an FPGA first mode, the Secure Device Manager initializes with the boot ROM. The boot ROM kick starts the whole process and knows the configure mode by sampling the M-cell pins. The SDM will first configure all of the I/O in the FPGA before configuring the FPGA fabric. Then it will load the first stage bootloader from the bitstream into HPS on-chip memory. The first stage bootloader runs, and part of its tasks is initializing the SDRAM, at which point the first stage bootloader loads the second stage bootloader into SDRAM. More HPS peripherals are initialized and the OS is loaded into SDRAM. After the OS is loaded, the HPS user application is run. With the HPS first mode, most of the tasks are very similar. SDM is initialized with the boot ROM. The boot ROM initializes only the EMIF I/O in the FPGA and then loads the first stage bootloader into HPS on-chip RAM. The first stage bootloader does all the same tasks, and then when the second stage bootloader runs, in addition to initializing the rest of the HPS system and loading the OS, the second stage bootloader will configure the remainder of the FPGA I/O and the FPGA core logic before releasing operation to the loaded OS. Please refer to the following references on this and the next slides. And now I will talk about the memory interfaces in both the FPGA fabric and for the embedded systems. The Zynq MPSoC FPGA fabric controller is a soft core solution where only the physical layer is hardened on Zynq MPSoC fabric EMIF. Other key logic blocks are implemented using core fabric. The Zynq MPSoC FPGA fabric controller supports the legacy protocols like DDR33L and DDR4 only. The fabric EMIF on Agilex 5 is a hardened solution. Every HSIO bank has the required hardened circuitry to support EMIF. Only the user design, for example the traffic generator, resides in core fabric. When the hardened solution is not used as an EMIF, the I/O can be used as general-purpose I/O. Agilex 5E series can support DDR4 and LPDDR4, whereas the D series can support DDR4, LPDDR4, DDR5, and LPDDR5. The Zynq MPSoC processor system hard memory controller uses hardened circuitry. It supports only DDR33L, DDR4, and LPDDR4 protocols only. The processor system external memory can only be implemented on its dedicated I/O bank, and you cannot use this bank for any other purpose when the PS memory controller is not used. The HPS EMIF in the Agilex 5 FPGA's D series supports DDR4, DDR5, LPDDR4, and LPDDR5 protocols, whereas the E series supports DDR4 and LPDDR4. The HPS EMIF uses the same hardened circuitry in HSIO bank as in fabric EMIF. Banks 3A and 3B can be used for implementing HPS EMIF. When not used as HPS EMIF, banks 3A and 3B can serve as regular I/O. When used as HPS EMIF, the HPS systems connects to the adjacent I/O banks via the multi-port front end, or MPFE. We will discuss more on how to make this connection in the Platform Designer in Quarbus Prime software later. For DDR4 HPS EMIF, the maximum data with that we can support is x32 plus ECC. There are some restrictions on HPS EMIF bank placement and unused pins. Only bank 3A can be used for HPS EMIF if the interfaces spans only one I/O bank. If the HPS EMIF spans two I/O banks, we can use banks 3A and 3B. You cannot use HPS EMIF and AVST by 16 by 32 configuration modes simultaneously as both use bank 3A. This table compares the maximum data width that can be supported on fabric EMIF. From this table, we can see that DDR4 is the only protocol that is supported by fabric EMIF on both Zynq UltraScale Plus, MPSoC, and Intel Agilex 5 devices. Agilex 5 devices do not support legacy protocols like DDR33L and LPDDR3. Agilex 5 devices can support LPDDR4, DDR5, and LPDDR5 while the Zynq UltraScale Plus, MPSoC does not. Note that DDR5 can only be supported on Agilex 5E series device group A. For DDR4, Zynq UltraScale Plus MPSoC can support up to by 64 plus ECC, while Agilex 5E devices can only support up to by 32 plus ECC. E-series devices do not support DDR4 by 40 configuration. Agilex 5 devices support up to 2 ranks. From this table, we can also see that Agilex 5D series devices can support DIMM and larger data width configuration. HPS EMIF support on Agilex 5 devices is slightly different compared to the fabric EMIF. This is due to the data width for one channel of HPS EMIF interface cannot span more than one I/O bank. For example, a single DDR4 by 64 cannot be supported because it needs more than one single I/O bank to implement all the address command lane and data lane. However, you can place one DDR4 by 32 in bank 3A and another DDR4 4 by 32 in bank 3B. 4-channel by 16 configuration for LPDDR4 and LPDDR5 uses both banks 3A and 3B. In this section, we will provide an overview on how to convert the Fabric EMIF IP from Zynq UltraScale Plus MPSoC to Agilex 5 devices. We will look at the external memory interface IPUs and how to map the competitor's IP settings to Agilex 5 EMIF IP settings. For Zynq UltraScale Plus MPSoC, there is a memory interface generator for each supported protocol. For Agilex 5 Fabric EMIF, all the supported protocols can be generated using the external memory interface's IP. You can locate this IP in the IP catalog under the Memory Interfaces and Controllers section, as shown in the right figure. In the next few slides, we will look at the mapping of various tab and IP. We will be using the DDR4 MIG IP as an example here. In the DDR4 MIG IP, there is a board tab that allows user to key in the board information. The Agilex 5 FPGA EMIF IP does not require this information. Hence, you won't find a similar tab in Agilex 5 EMIF IP. The I/O Planning and Design Checklist tab is providing some basic information and some links where a user can find additional details for the MIG IP. There is no similar tab in the Agilex 5 FPGA IP. In the Basic tab, the clocking section maps to the memory clock frequency and PLL reference clock frequency. The controller and memory options information in the Basic tab are mostly mapped to the high-level parameters and memory device preset selection section in Agilex 5 EMIF IP. Note that there is no equivalent entry for the mode and interface and the advanced user request controller options in Agilex 5 EMIF IP. In some protocol/device speed bin combinations, we will be able to achieve a higher memory frequency when enabling the asynchronous access. The controller options in the Basic tab are mostly mapped to the memory device preset selection. Let us take a closer look at the memory device preset in Agilex 5 FPGA EMIF IP. Memory preset is a file that contains all the parameters that describe the memory structure density, organization, and memory timing parameters. You can either select a memory preset from the memory preset drop-down list or use a custom memory preset less than 0.26 greater than. You can generate a custom memory preset file using the EMIF memory device description IP. Refer to the design example user guide, for example, on how to create a custom memory preset file. Each protocol has its own memory device description IP. Remember to use the correct IP to generate the custom memory preset file for a given protocol. In DDR4 SDRAM MIG, this AXI Options tab appears when you enable the AXI interface option in the Basic tab. In Agilex 5 EMIF IP, there is no equivalent tab. In the Advanced Clocking tab, the M&D section allows you to calculate the reference input clock frequency if you do not like the default frequency provided for the MIG. Agilex 5 FPGA EMIF IP does not provide this functionality. The System Clock option allows you to specify the reference input clock configuration. The valid options are differential or no buffer. Agilex 5 devices support only differential I/O standard on dedicated PLL clock input pin for EMIF IP, and we cannot change it. The only option that we can change in our IP is the input termination. The supported options are differential termination or no termination. The IP defaults to the input termination for the PLL reference clock to differential termination. You can change the termination value in the PHY input sections under the FPGA I/O tab. There is no equivalent section for additional clock output section, as the IOPL used for EMIF cannot be used for generating additional output clocks. The simulation option in DDR4 MIG allows users to select the simulation mode. The valid options are BFM and Unisim. The simulation option for the Intel Agilex 5 FPGA EMIF IP serves a different purpose. It lets you decide if you want to generate the simulation design example or not. The example design options in DDR4 SDRAM MAVE allows users to specify the traffic pattern to be used for simulation. In the Agilex 5 FPGA IP, this corresponds to the traffic duration to be used by the Hydra test engine program. This setting applies to both the synthesizable example design and simulation example design. For simulation purposes, it is recommended to select short, as this takes shorter time for the simulation to complete. For actual hardware testing, you may want to use medium/long. For EMIF pin assignment for a given interface, we only need to assign the pin location to PL reference clock and RZQ pin. As we cannot swap the address, command pin location, the fitter will be able to auto-place all the other AC pin locations. There is no harm in providing the pin locations for all the other address and command pins, but it is not required to do so. For DQ and DQS pins, do not assign any pin location assignment. Let the Quartus Pro software place the DQ/DQS pins to their default locations. If DQ/DQS pin swapping is required, use the swizzling flow. In this flow, enter the swizzling specification in the User Extra Parameters field when parameterizing the EMIF IP. Refer to Design Example User Guide for swizzling example. This pin assignment method is applicable to both Fabric EMIF and HPS EMIF on Intel Agilex 5 devices. In this section, we will provide an overview on how to convert the processor system DDR IP on UltraScale Plus MPSoC to the Agilex 5 FPGA HPS EMIF. We will look at the IP used and how to map the Zynq IP settings to Agilex 5 HPS EMIF IP. You can customize the PS DDR IP using clock configuration and DDR configuration page within the Zynq UltraScale Plus MPSoC IP. For HPS EMIF IP, we will need to create an instance of Hard Processor System and HPS EMIF in Platform Designer. Once they are created, we will connect IO96B signals of the HPS system to the EMIF instance, following the bottom right diagram. The PS reference clock is used for booting the system. It is also the default clock source for system PLLs. The frequency of the PS reference clock determines the actual frequency that can be achieved by the PS DDR memory IP. In Intel Agilex 5 FPGA HPS EMIF, we have a dedicated clock PL reference clock for the HPS EMIF. Its frequency can be set at the PHY tab in the Advanced Parameters section. This page shows the mapping of DDR configuration page to Agilex 5 FPGA HPS EMIF IP. The DDR configuration, DDR memory options, and other options mostly map to memory device preset selection or the options within the QPRS file. If the preset for the memory device that you are using is available in drop-down list, select the desired preset memory. The various entries have already been specified once you select the preset. Otherwise, you need to generate a custom preset for the memory part that you are using. The method to generate a custom memory preset file for HPS EMIF is the same as Fabric EMIF. The clocking option maps to the memory clock frequency in HPS EMIF IP. The DDR controller options maps to the high-level HPS EMIF parameters section in HPS EMIF IP. To recap, you can either select a memory preset from the memory preset drop-down list or use a custom memory preset. The custom preset file should be generated before parameterizing the HPS EMIF. The flow to generate the QPRS file is the same for both Fabric EMIF and HPS EMIF. You can generate a custom memory preset file using the EMIF memory device description IP. Refer to the Design Example User Guide, for example, on how to create a custom memory preset file. Each protocol has its own memory device description IP. Remember to use the correct IP to generate the custom memory preset file for a given protocol. We will take a close look on how to map the various entries in the DDR memory options and other options to the EMIF memory device description IP. Just to reiterate, we use the memory device description IP to specify the value and save it as a QPRS file. If we are using the preset from the drop-down list, the HPS EMIF IP will use pre-specified values. The options shown here are the memory timing parameters. In memory device description IP, the recommended flow is to specify the memory clock frequency and select the correct speed bin for the memory part that you will be using. Based on this information, The memory device description IP will auto-compute the other timing parameters and advanced timing parameters. If you want to use a different value, you can uncheck the box and manually enter the value you want. The mapping for other entries are shown. It is not required to enter the bank group width and address width in the DDR4 memory device description IP. The memory device IP is able to compute the address width based on other high-level parameters. The dual rank option and the address mirroring options map to the memory ranks and command address mirroring options under the per EMIF parameters section in our IP. Now we take a close look on how to create an instance of HPS system and connect it to the HPS EMIF in Platform Designer. The steps listed here demonstrate the settings in the HPS system that are related to the HPS EMIF. The FPGA to SD-RAM subordinate settings are optional. It is only required when you want to enable the FPGA to SD-RAM bridge. In the SD-RAM tab, enable the AXI interface and select the EMIF topology for your system. The HPS EMIF IP is very similar to the Fabric EMIF IP. Parameterize and generate the HPS EMIF IP. Once both IPs are generated, connect them using the connections shown here. Note that this figure only shows the IO96B signals from the HPS system. Be sure to check out the reference documents that I have listed here: Agilex 5 FPGAs and SoCs device overview, and application note 307 Altera FPGA design flow for AMD's Xilinx user. Thank you for listening to this conversion guide. We covered various aspects of the conversion process that are listed here. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5-minute quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live, instructor-led course presented either in person, at an office local to you, or virtually over the web. All instructor-led courses have hands-on labs, exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages called landing pages dedicated to specific FPGA technology like and high-speed interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. This concludes the training. Thank you and have a good day.